Our next example is going to be a little bit odd. We're going to look at integral polynomials in the transcendental number pi. So let me just remind you that pi is transcendental. And roughly what this means, it means that if you have, well, over q and z, if you have any polynomial that's non-zero, and you plug in pi into it, you will never ever get 0. So i.e. if we have a non-zero polynomial, then over q, then p of pi is not 0. So it does not satisfy any algebraic equation over q. All right, so what does integral polynomials in pi look like? Well, it's like we're taking z and we're going to add in pi. But we want it to be a ring. So if we add in pi, we're going to have to also add in pi squared. And if we add in pi squared, well, we're probably going to have to add in pi times pi squared, which is pi cubed, and so on. And we should also be able to multiply those by integers. So we should get integer multiples of powers of pi. But we also need to be able to add. So we're going to get formal combinations we're going to get sums of integer multiples of powers of pi. And if you write that out, you get exactly integral polynomials in pi. So that's how this comes about. So the a's are some integers. N is some natural number, maybe 0. So let me write n0 to mean including the natural numbers. And that's what elements of this set look like. So this is a weird set. So for example, 1 plus pi is here. What's another example? I don't know. 2 plus 6 pi minus 9 pi to the 4th plus 2025 pi to the 2025. Right? That's also here. And that's as good as it gets, because remember, pi is transcendental, so you can't like collapse powers of pi. This is what this looks like. So that's what elements of this set are. Let's check that this is a subring that's not a subfield. I think we can immediately argue that it's not a subfield because we still don't have multiplicative inverses of elements like 2. Okay, so proof, 2 is certainly here. It's like 2 plus no powers of pi. And 2 inverse is not going to be there. 1/2 is certainly not an integer. It's certainly not an integer polynomial in pi. So not a subfield if it is a subring. Definitely not. Okay, let's show it's a subring though. So we prove, well, what are we going to do? We're going to apply the subring test. Sorry, that's one of my dogs chewing on some cardboard. Okay, so we apply the subring test. What does the subring test say? Well, we need to make sure the complex number 1 plus 0i is here. So is the complex number 1 plus 0i, which is just 1, is that a polynomial in pi? Yeah, it's just got the constant term. There's no powers of pi that we add on. So that's good. If we have 2 polynomials in pi, we have to check that their difference is there. So let's take 2 polynomials in pi. That's one of them. And then here's another. Let's use b's. And it may not be the same, degree in pi. So these are polynomials in pi. And then we have to check their differences there. Now, without lots of generality, let's suppose that n is bigger than or equal to m. I don't know which one of these powers is bigger than the other, but we're going to make this assumption that the first power is bigger than the other one. It's easy to fix the proof if it's not. Then the difference, we can think about the difference as like I go up to am because the degree n is bigger than or equal to m. And then like am plus 1, oops, the next index, pi to the m plus 1, all the way up to an pi to the n. And then from that, we're going to subtract off b0 plus b1 pi, b2 pi squared, all the way up to bm pi to the m. And this is where it's important, where we made a choice. There are other ways of getting around this choice that we'll talk about later in the course. All right, so how do you subtract polynomials? Well, you subtract their coefficients, right? So a0 minus b0, a1 minus b1 pi, a2 minus b2 pi squared, all the way up to am minus bm pi to the m. And then after that, there are no more b's, so it's just a's. And is that, again, a polynomial in pi with integer coefficients? Well, all the coefficients are still integers, because the difference of it, if you subtract two integers, you still have an integer. So certainly that's true. All right, so that's closed under subtraction. And now we need to do closed under multiplication. Now, I'm going to do it's kind of a hand-wavy proof here, because the actual proof involves a little bit more notation than what I'm prepared to talk about right now. But if we took two polynomials in pi, and we multiplied them this time, it doesn't matter. We can still assume that n is bigger than or equal to m, if that is helpful. How do you multiply polynomials? Well, we have to distribute. a0 times b0 is going to be the new constant term. What's going to be the linear term? So how do you get a linear guy? Let me use a laser pointer. You take a0 times b1 pi and a1 pi times b0. That's the only way to get a degree 1 term in pi. So a0 b1 plus a1 b0. Then how do you get a quadratic term? Well, you can do a2 pi squared times b0, you can do a1 pi times b1 pi, or you could do a0 times b2 pi squared. So you're going to get a0 b2 pi squared. Oops. a0 b2, a1 b1, a2 b0. And those are the ways you can get pi squared, and you keep doing that. And there's a general formula that we'll talk about later. And then the biggest degree term you're going to get is this last term. Okay. So what's that? That's an bm pi to the n plus m. Now the point here is that what we get are products as our coefficients are finite sums of products of integers. And that's still an integer. So this is certainly still in z adjoint pi. So let's see, we did close under subtraction, and this is closed under multiplication. Thus, z adjoint pi is a subring of C. It's a weird subring. Let me also notice that E is also transcendental. So that's the end of that proof. But as a remark, E is also transcendental. So Z adjoint E is also a subring of C. Polynomials in E, and the proof is exactly the same. What do? You do this, but you replace all the pi's with an E.